Welcome to Digital Currents, brought to you by Morgan Creek Digital. I'm Xavier Segura. Each episode, we spotlight the topics and people changing the tech industry with a focus on AI, blockchain, chips, and big data. Thanks for listening, and please make sure to subscribe if you like what you hear. And remember, stay current.
Mark, we are back at it, and this time with a guest, Will Zhang, who is a partner at Quantonation. And I'm so excited to introduce Will. Mark, allow me to join and welcome him with you. Welcome, Will.
No, thanks for joining us.
So, Will, I'll do the embarrassing part off the jump about reading part of your amazing background, but I want to hear it in your words as well, but we'll just give a little bit of some of the elevator pitch kind of style introduction. So you're a PhD, so should I call you Dr. Will, Dr. Zhang? Just Will? Okay, great. That's fine. And so basically focusing in on this global early stage ventures on quantum and deep physics. And so, prior to that, really working actually on the banking side in Goldman, but focusing in on all the advanced computing and quantum research as part of how that even launches things like Rigetti and their cloud service offerings. So I think that, now we're at a point, I'd say, Mark, where we're starting to understand quantum a little bit more, but just wanted to welcome Will, and maybe we'll start right there at the beginning. Just fabulous background. If you could just kind of like walk us through a little bit more about you and kind of how you got into what is admittedly something quite technical.
Yeah, sure. Well, I am a technologist by background, and my whole career has been in quantum technologies and advanced computing technologies. And I got into it as kind of more of a kid. And the thing that attracted me to quantum tech, and sort of maybe it's good to back up, quantum technologies is about using quantum mechanics in new ways. Quantum mechanics has been around for 100 years, and it matters for technology. Lasers, transistors, GPS, all these things work using some aspects of quantum mechanics. But in the last 15 years in particular, and a little bit longer in theory, people have been inventing ideas for technology that use some of the more sophisticated and weird parts of quantum mechanics, like entanglement and superposition and stuff like that. And there's now an industry that's starting around products with these capabilities in computing, sensors, networking, materials, all that kind of stuff. And when I was a teenager, I started to get into the quantum computing side of things. And the thing that really appealed to me about the space is that you get to do two things at the same time. So the first is you get to ask pretty fundamental questions about the relationship between physics, quantum mechanics, and like information theory. And it turns out that physics doesn't always limit the kinds of computations we could do. Actually, physics can do kinds of computations that we don't really understand, or at least it took a while for us to understand it, and that's the field of quantum information theory. And then at the same time as you get to work on sort of fundamental questions like that, you get to build technology that could have really, really big impacts and build tech that has capabilities that we wouldn't have had if quantum mechanics wasn't true. So that's what hooked me. And I started working on, as I did my undergrad at Yale, started working on superconducting circuits, which is one of the ways of making quantum systems. I was really learning, but I got really lucky to be in a lab where people were inventing what's become a very core technology for the industry. Then I did my PhD on the algorithm side in Oxford in quantum algorithms, which is sort of like, how do we use quantum computers to do interesting and novel things? How do we take best use of quantum mechanics to be productive? And then after that, I was part of the initial team at a company called Rigetti Computing, which is which is now pretty big. It was three people in an empty warehouse when I showed up, and that was really fun. I mean, we were really the first startup building these digital quantum computers. When we talk to investors, it's a lot bigger now, but I never heard of qubit, I never heard of quantum computing. It's
What
weird.
was that like? What was that like? Kind of going in, it's a three-person company. I'm sure, given the background and the expertise, speaking to mom and dad, you could have gone anywhere, and you go and you choose this three-person company working on something that is basically out of Marvel Studios. In terms of this technology that is a fantasy in some ways because we don't see the direct application yet in terms of revolutionizing computing, although we can argue that we are starting to see that in many ways. And I'll remind Mark, you heard the story earlier this morning, but I did on my flight back home last night, see Oppenheimer, and it was all about the kind of discovery of Einstein and the quantum layer and how that led to real impacts, albeit for destructive means. But here we're talking about ways that this can potentially change the way that we send information and receive information. So when you're looking at the three-person company, like what did you see there of substance in such an early state that made you want to jump in?
Well, I had all the technical insider information that you might want to have, with that, Chad, who had started the company, had been a postdoc in the lab I worked at as an undergrad at Yale. And so I knew, what he was building. Like when I originally got introduced, like he wasn't pitching me, like I kind of knew where it was going. And this approach with superconducting qubits was intriguing and had been getting a lot of traction because they figured out how to make a chip-based technology that could still do quantum stuff. And the challenge of a quantum computer at a very high level is that quantum mechanics has these subtle powers, but like we don't see them in the everyday world because when systems get big or hot, the quantum mechanics gets kind of averaged out. So you need to have a system be isolated in order to see the quantum behavior and make use of it. But, a quantum computer has input and output. So like, how do you get those two things at the same time? And most people had been thinking about starting with a quantum system, like a photon, like light particles or atomic levels or ion levels of an electron in an ion, and then trying to figure out how to control them. And superconducting circuits went the other way, and they said, let's take something we know how to control in fab, in this case like an RF microwave circuit, and then like cool it down, make it superconducting, and it turns out, even though it's kind of big, it behaves quantum mechanically.
Maybe step back just for 1 second. So when we think about computing, right, we meaning collectively all of us who grew up in computers, the term computer applied to humans, right? There were no machines to do computers. A computer was a person who would like physically change like numbers on a big board or write things on a chalkboard. So those were computers. And then computing systems came along, and to boil it down, I guess it's basically difference between two states, right? 0 and 1, black and white, whatever, on and off. And by having a combination of those ones and zeros, those binary, units, we can essentially create magically, all of like the images on our screen right now. It's just a bunch of ones and zeros in a particular order. I still don't understand how you unpack all those ones and zeros to make it have red and green and blue and the 3 shades of blue that we're wearing today. And we got Notre Dame blue, we got a little Florida blue, we got some Carolina blue, which I appreciate as a guy sitting in Chapel Hill. So that's a long-winded way of asking you. So we have bits and bytes that I think most people are familiar with, but then we go to this quantum realm. What's different and why is it so important?
Yeah, so even at that basic level, things change when you go to quantum computing. And that's different about quantum computing compared to other ways of accelerating computing, like a GPU or even something sophisticated like a neuromorphic computer that's inspired by the brain. Like that's all using sort of what we call classical physics, non-quantum physics. And there you're working with zeros and ones, fixed digital numbers. But in a quantum computer, your basic unit is not a bit, but a quantum bit, which we shorten to qubit, and it has some special properties. So it can be, in some sense, 0 and 1 at the same time. And to give you like an idea of what that might be, so one way you could build a quantum bit is to take a particle of light, like a photon. It's moving through space. And when a photon moves through space, it spirals like a football. So like it can be spiraling right, or it can be spiraling left. Like that's its polarization. And if it's a football, like it's either spiraling clockwise or counterclockwise. Like,
Yep.
That's it. But if it's a photon, it can be doing a mixture of the two of them at the same time, which is this special quantum thing called superposition. And when you start adding together multiple quantum bits that can be in superpositions, you can have more sophisticated computing capability. And we can dive into math if you want, but like the core thing is that the very basic unit of computing has changed. Like it's not about probabilities anymore. It's about this generalized version of probabilities called amplitudes, where you get negative probabilities. Like it really changes the basic stuff.
Fantastic. Thank you. Because I think at the end, most of us, have a very cursory understanding. We hear the buzzwords, we hear people talk, but, and we hear people talk about, quantum's going to do this or quantum's going to do that. At the end of the day, we have to think about what computers are intended to do, right? To do calculations, to do storage and retrieval, to do processing of data. And this whole new era of computing, I think, takes us in some new directions that I think we'll probably talk about here.
Yeah. And to that point, I guess, Mark, we've seen, Will, some of this story before, right? Where it's like, I saw this with mobile for a while. It was as an investor, an operator, it was like, 2016, or you'd say 2008 was the year of mobile with the launch of the iPhone. Then it was like, 2012 with like the merger of Alphabet or Google at the time and Android. So it's always the year of something. And so I think there's no better year than to describe like the year of quantum, right? Where we're seeing a lot of these big companies make headlines to do things that might excite consumers, but kind of missed the mark a little bit on actually delivering some systems. But that's not kind of the areas that you guys focus in on over at Quantonation. So I was kind of, what caught my eye was, the latest, headline on PsiQuantum and their successful raise at $1 billion at $7 billion valuation. So this is a kind of an interesting way to actually bridge this gap, right? So it's advancing photonic fault tolerant, quantum computing, and you're trying to get towards a way to actually make this live, right? Where you're trying to get toward that million qubit system, or the Goldilocks zone, right? When you kind of get enough of these really hard types of matter to actually perform a function. Because right now we kind of run into this problem, as you've probably seen, well, where we keep thinking, the quantum computer will replace the need for a regular computer. Or we've seen kind of the two, at least now, operate side by side, and there's some things that like the classical analog computer will do, and then whereas a quantum inspired device or computer will operate at a entirely different kind of speed and ability. So maybe beginning with kind of that live example, because it had the who's who from Temasek to BlackRock involved, and y'all as well. So does that kind of really mean that we are now in the year of quantum, kind of to bring it all back with deals like this?
Yeah, I mean, there's been a lot of growth in the quantum technology sector, but this might be a year of quantum, but it's not the one. I mean, we've got a longer runway for how this industry is going to develop. I mean, as exciting as it is now, there's so much to come. And maybe just to set some context, I'm also now a partner at Quantonation. We're the most active early stage venture fund globally in quantum tech. And part of an answer to your question is like, why is that the right thing to be doing now? And the short answer is there is an industry, and there are some incumbents. There's about a little over 40 billion-ish in like private plus public market cap now in quantum tech. When I joined at Rigetti, that was approximately zero. I don't know, maybe like 50 million or something like that. So there's been this first wave of basic technology development that's already got people excited. And now we're asking questions like, how do you bring that to market? How do you generate revenue? How do you make them cheaper and faster? And there's a lot of ideas about how to do that. Maybe I'll pause there, and then you can tell me which direction you want to go. You want to
Well, now I was going to say, can we back up for a second? So at Yale, you were working on, quantum theory and quantum mechanics in labs, and that led to joining Rigetti. And Rigetti, maybe it's not a household name, but anyone who's followed quantum, particularly this year, certainly knows that company and the public and the rocket ship ride that those stocks have. Actually, it's been a bumpy rocket ship ride with Jensen's comments and things. But at the end of the day, explain a little bit about what was Rigetti trying to do? What was the goal of you guys in the warehouse?
Yeah, so I was leading software and then product, and our goal was to make useful quantum computers and to make the first ones. And what the innovation we were kind of leaning on had two prongs to it. Now, this is a while back. This is 10 years ago. This is 2015. It took a while for things to kind of percolate. But one was we had a hardware technology, these superconducting qubit hardware technologies, that was it was chip-based. And so it seemed more engineerable and more manufacturable than other approaches. So there was a hardware innovation there. And the other innovation was on the programming side. And there had been maybe 20 years of theory work about how you can use quantum computers, but most of that thought had been about using quantum computers as sort of relatively standalone devices. And there was a new set of ideas called hybrid quantum algorithms or variational quantum algorithms, which is more about how do we use quantum computers with classical computers and maybe make use of them sooner, not needing to wait for ones that were quite as big as we predicted before. And so those two things came together, and we said, well, all right, let's try and build and ship things to the market sooner than other people, and leverage those two innovations. And I think the positive thing there is that a lot of those machines are now getting built, and a lot of people are building them, but it didn't happen so fast that the other approaches died off.
Right.
And what we have now is less of a convergence on, this is the one way to build a quantum computer, and actually a world where there's a lot of approaches to building quantum computers that are really competing over different kinds of trade-offs. We have a portfolio.
Got it. All right.
So then maybe bridging those two and kind of some of the earlier points about, some of the new deals, and is this kind of the year or just another year in what will be a long journey in the transformation of technology, maybe talking a little bit about Quantonation's thesis and the idea of focusing on deep tech and quantum and kind of how that fits in to some of, the opportunities that you're looking at, and maybe what excites you with where you're at today.
Sure. So we're what I'd like to call a physics tech fund. And I mean that in a little bit of an analogy to biotech, which is now a category that people know, right? What do you got in biotech? Well, you got GPs, VC, who have PhDs, who go really early, they get tech risk, they read the science papers. Sometimes they do a lot of team assembly because a lot of the initial founding teams are sometimes super academic, and so they need a little help to kind of form up at the start. That model shouldn't just work in the life sciences. And in particular, we think there's some great reasons to look at doing something like that in physics departments and in computing hardware. And so that's what we do. And there's a couple big themes in physics tech right now. One of them is obviously everything in quantum technologies. There's quantum computing, the sensing and the networking. There's other things in quantum tech besides computing that are pretty big. But there's other ones too. I mean, everyone's getting back into nuclear these days. That's definitely physics tech. There's other kinds of computing that aren't quantum but are interesting, like analog or optical or probabilistic, which have some interesting applications in ML and in huge data centers. There's physics tech all over energy and in space and propulsion, all this kind of stuff. And And so we see the opportunity to do, there's a history of physics tech mattering a lot, right? Like from the transistor to nuclear power to, whatever, rockets. And so we're carving out this new category. And one of the themes we're investing heavily in is the quantum tech theme there.
Yeah. And so to that point, Will, Mark and I often joke a lot about AI because it's very easy to do, as it's, most of the investment dollars, I think like 60% of them this year are going towards AI deals. And in some ways it's described, as kind of a bubble. In other ways, we like to describe it as the 70-year overnight success story. And so when you kind of think about quantum as also taking 70 years, developed, before the wars and kind of to where we are now in terms of being able to refine it, how do you kind of think about this life cycle, and how do you weigh this kind of long-term timelines against, actually delivering things like returns to investors or just milestones in companies to kind of actually advance the technology? How do you guys think about that as a fund?
Yeah, so you're kind of commenting on how a sector evolves as a whole wave, but we're a venture firm. We invest in outlier individual companies. And so it's not that every one of we're not investing in companies that have a 70-year timeline.
That would not be a good size for a fund, right?
We got a 10-year fund. It's like not, the fund structure is pretty standard. So the magic is, how do you find stuff that has the good things about physics tech, about quantum tech, which are really defensible, really unique, improved capabilities, but also fit a fun timeline.
Right.
And you can fund his venture. And if I had $50 billion, like, I actually think I wouldn't be able to, that's too big for where the sector is right now. But it's growing quickly, and I think we're right size for a lot of those opportunities. Does that make sense?
Yeah, no, it makes total sense. And I think, whether it's quantum or whether it's fintech, which is something much more commercially available now, you're still dealing on a set of principles, figuring out ways to improve on product, right?
Yeah, and let me, like, to what you're saying about the 70-year journey, like, in a lot of ways, AI now is a story about, guess what I'm saying, physics tech.
Right.
Because as much as like innovations on the software and algorithm side are really important, and of course they are, transformers, those kind of stuff, like, neural networks have been around for a long time, and what changed is fabrication, hardware, scaling and architecture, and like what let us do next generation EUV optical lithography fabrication, ASML's crazy laser sources, deep physics tech stuff. And so if you build like the core, I think often like a very core mover of civilizational advancement is unlocking fundamental physics tech improvements, and then you can build, all the software and stuff kind of on top of it.
Yeah. So should we be thinking about, and so what maybe a lot of investors think about where we begin is thinking about like this Goldilocks zone, right? Of like the 10,000 qubit as being the plateau. And as we kind of increase there, we can do more and more advanced things. A lot of the release and the hoopla is around smaller number of qubits, like 100 or 300 as a more of like a proof of concept, but they can do really interesting things, but they're not always practical. Do you guys kind of think about those same numbers, or are you operating on a different standard when you look at, I'm going to be really excited about what this company is about to do?
I don't think we operate on a different standard. Like we operate on a venture standard, which is like, we want companies with great teams, differentiated technology going after big markets. Now, when it comes to how big of a quantum computer you need in order to attack a big market, the jury's kind of out. Like, I don't think, we know that 10 qubits is not enough. But something that happened in the last decade that I think has surprised people a bit is that quantum computers with only 100 pretty bad qubits, we're talking like really high error rates, can actually do some computations that supercomputers can't. Now, how useful those computations are is both a theory and a marketing question, and a market question. But that came earlier than people thought. The algorithms we could prove would be useful really need, maybe 10,000 qubits with error rates of, I don't know, 1 in 100,000, 1 in a million, 1 in 10 million, maybe even a little more. And so that's one end. And then it turns out we got kind of actual demonstrations of maybe esoteric problems, but with like 100 qubits with 1 in 1,000 errors. And there's this like big gap in between. And that's what the vendors and the application developers, like the quantum computer ecosystem, is attacking. And some people are attacking it by saying, let's wait, let's get big at scale. And some people are saying, let's do heuristic experiments with what we have now and see if we can find surprises. And I think you want to have a portfolio across that too.
So, Will, let me ask a question on this that can explaining some terms. So you said something about error rates, which I want to circle back to, but when I can not, yeah, I think back, you're causing me a little stress that when I went to college, I thought I was a pretty smart kid. I show up at college and my first test was in physics. And I'd never gotten a B before in my life. And my first physics test, I was like, hey, teach, you forgot the right-hand side of the A. And I got the big F. So I didn't even know what I didn't know. It was so bad. So physics, so I'm not a physics guy, obviously. But I think I understand the difference between a 1 and a 0, right? States 0 and 1, off and on, and how we use those off and on states to create things, right? Numbers, letters, outputs, whatever. And there's no error, right? It's either a 0 or a 1. Now, maybe that's not true, but in my mind, right?
Yeah, there are. Yeah, you still got, regular computers got errors too. And in fact, as data centers get really big, the error rates are really low in regular computers, but because data centers are so big, the errors are coming back.
Okay, that's a really important point. So again, in my mind, 0 and 1, no errors. But you're saying no, there could be some errors. But in something that can exist in multiple states, there's again seemingly potential for an error. Like if I ask what's 2 plus 2, I need the computer, whoever that's physical human or whether it's a machine, to deliver 4 every single time. But if the physical state of that qubit is, plus or minus some error rate as you describe, and maybe I'm not thinking about this the right way, but if it returns 4 99.999999% of the time, that's okay. But if it's 98% of the time, that seems less good. Am I thinking about it wrong, or how do error rates come into play?
Yeah, there's actually 2 kind of levels. So there's errors and then there's determinism, and there's sort of different things. And determinism is that like you run, you always get the same output as opposed to getting a probability distribution over outputs. And actually, because of AI, I think everybody should be getting kind of used to the fact that like non-deterministic or probabilistic computing where you get different answers is totally fine. Like LLMs give you statistical outputs. Like they don't give you the same thing all the time.
Thank you for saying that. It's such a funny thing that if someone types something into ChatGPT and it gives you an answer, like, oh, that's the truth. I'm like, no, that's a probability distribution outcome based on what it thought the next word should be in a sentence. So,
but it's still useful, even though it's
still useful. No, it's still useful. Yeah.
The thing you want, if you have, is that you get the right distribution. You're sampling from the right distribution. And so errors come in when you're making the wrong distribution. So quantum computers, quantum mechanics is probabilistic. So kind of like an LLM, like when you program quantum computers, you're getting back a sample of the answer. But you want that sample to come from the correct distribution.
Okay.
And in early quantum computers, like in early regular computers and really big regular computers, the actual operations that you control the quantum bits with sometimes go wrong. And that is the error rate. And if you have a high error rate, you can only run short programs because if you have too many operations, the errors kind of squirting up. Yep. So as quantum computers get better, the length of programs we can run gets longer. And, it's all about predicting like when you're going to unlock different markets as you get to run bigger and bigger programs.
Got it. Okay.
Yeah. And so, Will, we're talking a little bit earlier about,
how there's certain potential breakthroughs in this, long journey, this evolution of the sector. And one of the things you mentioned did catch my attention, and the ability to bring quantum technology in a chip infrastructure. And so normally that rings bells in my head when I'm thinking about Dirac, which is kind of one of our mutual investments. So I think within that type of investment, it helped us cross the chasm. That was our first entry into quantum. And it took us some time to kind of understand this. Tell us a little bit about them and kind of what helped get you across the finish line to think, hey, this can go from the theoretical to the practical and have this new change on silicon, which nobody's really ever done before.
Based out, they were originally founded in Sydney. Now it opened up in the US as well. They're a global company first. So I talked about Rigetti, and one of the original things there we were excited about is like, oh, you can make quantum processors on chip. But that was a chip. Yes, it was a chip, but it was a non-normal kind of chip. Like you had special fabrication procedures that you had to do, some special materials. You couldn't make it at a normal foundry. Actually, pretty early on, we had to build our own fab, which is, I mean, not like a $10 billion TSMC fab, but sort of our own version internally, which is expensive to do.
Sure.
And other people who were taking that superconducting approach have kind of had to do the same thing. IBM and Google are doing kind of a similar thing. Google had a big announcement last fall about Willow, and a lot of the improvements in their new chip they disclosed came from them building their own fab. And, Google's got a lot of resources to do that for making these special kind of chips. But gosh, like, wouldn't it be better if you could make quantum chips at TSMC or at Samsung or Intel with what's called CMOS, semiconductor fabrication, the normal way of making chips with as few tweaks as possible. And that's what Dirac's figured out. And it's an old idea. People have, it's kind of obvious that like that's what you want to try and do. And people have been trying to do it for a long time, but only recently has it started to work. And, we knew about physics, and the founders have been doing this for a while. They've been funded by the U.S. Government for a long time.
Mm-hmm.
And it's kind of a combination of their own innovations and also the foundries, the regular foundries, TSMC, Samsung, Intel, kind of also getting better. So like they kind of started to get good enough that you could start to do these kind of quantum relevant designs. And so Dirac's the only company in the world so far that's shown good quantum bits, like ones that you could error correct and start to scale, made from a third-party commercial CMOS foundry process. And so not only does that mean that you don't have to spend the capital to build your own fab, and you get to take advantage of, I don't know what it is, the 10 trillion that's been spent in developing classical foundries, but also it means they're much smaller and cheaper. So like those superconducting qubits we were doing at Rigetti, you can get maybe like 10,000 on a wafer. You can get millions of Dirac qubits on a little chip. So that's a pretty special advance, and I don't think everyone in the ecosystem kind of knows that about silicon qubits, which and about Dirac's technology. They're sort of slowly finding out, oh, this is starting to work. And that's part of why we got really excited. And, maybe that's part of what got you guys interested in taking a jump too.
Yeah, absolutely. I'd say it was one of the few examples that we saw a path towards commercial viability, just based on the way that, computing works today and how we've all been complicit in having these big data centers on all over the country, all connected underwater with these massive sea cables, kind of making the system works back and forth. And so to kind of have a technology that is a breakthrough technology, which still incorporates a legacy infrastructure just in silicon and chips, can, in my mind, bridge that gap between, we want to travel at the speed of light, but we still need, conventional metals that we know of here on Earth that can resist that heat, to kind of bring it back to your physics background, right? So the same idea, we want to be able to get to quantum speeds, but if we cannot have just an infrastructure that can support that merger between what classical computing is doing to pull up like a a script or to pull up, a command terminal to program what a quantum system is supposed to even look at, that's going to create some friction, and that's going to reduce people to say, well, I'm going to use quantum for this, and maybe I'm not going to dedicate my resources fully towards what it could do in the future. So that was a super like aha moment for us. And the fact nobody was doing it at that scale was wonderful. I mean, one thing also too, Will, maybe you can speak about is like, what partnerships in quantum do research universities play? In particular within Direct, where they had the partnership in New South Wales, and kind of what does that make it different from something like AI, which is still very computationally intensive, but is in some ways able to now step outside of the university setting, whereas within quantum we are still seeing a big relationship there between kind of some of the research centers and some of the best startups.
Yeah, I actually think that's just the difference between software and hardware. In that, a lot of the AI stuff, like it's just the people moving. So they're not dependent on a lab that's got a lot of capital investment that can then be kind of non-dilutively accessed if you keep the partnership. And so a lot of the hardware companies, the quantum companies are hardware companies, and so they want to, when they start, not spend their first seed round rebuilding something they already have at the university campus. But the quantum software companies, they can move. So I actually think the distinction is more of like a hardware software kind of thing.
No, that makes sense, and that'll ultimately help bring down R&D costs. It'll help you get to market a little bit faster, and help you realize it in a 10-year fund rather than a 70-year fund. So maybe one quick question before we go to the real fun part of our conversation in the lightning round is maybe just getting your take, Will, on some of the more commercial applications of quantum. Where do you kind of see today as the most viable and in the short term real world applications that get you the most excited about? Was it something like pharma, or we've had a lot of IPOs recently, maybe it's finance. What is kind of the area that gets you most excited?
Yeah, so I mean, we've been talking really specifically about quantum computing, but there are these other things in networking and sensing, this kind of stuff, and they're a big part of our portfolio too. So maybe I'll give an example of something that's kind of different and has a different shape. So we have a company in our portfolio called Multiverse Computing, and they do something that we call quantum-inspired computation. They're a software company, and there are algorithms that you'd want to run on a quantum computer that you would get a speed up from, but the quantum computer is not good enough. And so it turns out sometimes there are ways to kind of approximate that algorithm and run it on normal hardware. Now, you don't get all the benefits that you would get if you had a quantum computer, but you get some. And sometimes those some benefits are enough to build a pretty great business. And that's what Multiverse is doing. And the breakout product is one for large language model compression. So you take one of these LLMs and you can compress it by 80, 90%, cutting the energy costs and increasing the processing speed while maintaining performance, basically using tricks that come from quantum algorithms. And with that, they've built a pretty big business doing, I don't know if they're public about their revenue numbers, enough to raise a $215 million Series B earlier this year, not based on we're going to make quantum computers in the future, based on this is our scaling AI business today. And we led their pre-seed and seed. There's other examples, like we have a company called Qblocks, picks and shovels company. They sell control electronics for controlling a lot of this quantum and physics tech. Mm-hmm. And they bootstrapped to 100 customers and more than 10 million in product revenue before taking venture. And that's in quantum tech. And people don't always know that something like that's possible. And so when I was saying that kind of the secret sauce of us is finding the venture bets that have the good quantum parts together, like it's looking for those sort of unique opportunities like this. And those, both of those are not only kind of being used today, like totally in production.
No, I love that. And it reminds me a lot, the idea that you mentioned about quantum inspired. It kind of reminds me of crypto inspired, which is a moniker that we also started to see a lot in the early days of our industry. So we operate, as you know, in ABCDs, artificial intelligence, blockchain chips, and big data. And so early on in the fund life, you'd see a lot of companies, they would slap on, the word crypto, and their valuation would really skyrocket. So it became kind of difficult to, suss out the wheat from the chaff. And eventually the ones that were focused on, this, I'd say Web 2.5 were the ones that were getting real revenues because they could actually, solve a real problem. As we got further in technology, you had some real pure play companies that would, be front end and back end fully on blockchain. And I expect, in the coming years, that's probably what we'll expect to see also with quantum. So enough of that, and we'll probably go to the real fun part here of the internet famous Mark Yusko lightning round. Mark, take it away. Let's get to know Will a little bit better.
All right. So, Will, it's just softball questions. Feel free to answer quickly or spend some time on them. But, the first one is, what personality characteristic do you think makes a great venture capitalist? You've transitioned from researcher to business, builder to VC. So what do you think makes great VCs?
Yeah, good point. Maybe you should be asking a guy who does fund of funds. I think my job is picking great founders.
No, exactly. Oh, I think that's it, right? So the ability to identify great founders, right?
Yeah. And well, look, I'm not going to generalize too much, but I want to tell you a little bit about for me, what's a leading thing about why I'm in VC and what I like about it, which is, when I was ever getting to join 3 people, left at 150. I did 300 interviews with people who had way more career experience than me in 18 months, and part of what was so special to me about that was the talent identification part of it and the chance to give people with a great certain kind of talent a platform to realize it. And, that there's a bit of the ex-Spaghetti Mafia as well. That's a big part of being connected in now. And finding founders is like that. And look, I think you have to, particularly at the early stages, different than growth, but at the kind of thing that we do, which is pre-seed and seed, certain kinds of technical founders, you've got to be really interested in them as people, and you've got to be evaluating them as people because founders are not interchangeable in any VC, but in particular when you have founders who have a unique technical skill set, like we get all the time, they're really irreplaceable. So you've got to look at them as people and see if they're going to be able to build that business.
No, 100%. Look, I talk about it all the time. Talent identification to me is the great thing. And it's also the best job in the world, right? To get compensated to, talk to the smartest people in the world and give them capital. It's awesome. So follow-up question, so related to that is, okay, what is it that makes a great tech entrepreneur, tech founder?
Yeah, in our case, I think it's, you need ambition.
Okay.
And I think the levels of ambition that people think of when you say ambition are, or maybe it's more unbounded than they realize, right? We want people who ideally are reading the history of Intel and going, there's no quantum Intel yet. I'm going to do that.
Nice.
There's going to be.
Yeah, there's going to be. No, you're right. You're absolutely right. That's perfect.
And they need to pair it, but they need to pair that with the other side of the coin of that is you can't do it on your own. So they need to also be able, you want to be able to identify their talent. You want them to be able to identify talent.
Yeah, good team builders.
So I think the team builder part is really key. I mean, of course, there's the idea and the market and the technology, but people with enough ambition and the team building aspect who are coachable, and I'd say those are the 3 things that pop to mind.
Yeah, and it's not like I saw this funny meme the other day about baseball, right? And had all the positions on the baseball diamond, and the pitcher is always the coach's kid, and the center fielder is the fastest kid, and the first baseman is the tallest kid. So there's no mimetic opportunity for picking a team in tech. So you talked about seeing the quantum light, so to speak, and kind of why you got there. So kind of already answered that question, but what is it about quantum that you think makes it the best investment opportunity right now?
Oh, well, it's the timing. It's a value question. Buy when it can be huge. There's no other theory of physics. We're going to use quantum mechanics. The new stuff's coming from that. And the investment is $2 billion a year now. I think this is going to be a banner year. Maybe we'll hit $4 billion in private investment. 5 years ago, it was nothing. AI is $200 billion. Okay, so quantum's got that ramp to go through. It's mentioned on the lips of heads of state, AI and quantum, and
Yeah.
it maybe blockchain is the other, but those are already, that's trillions of dollars. So what's the one of those that has that level of impact that you can buy early now? And that's quantum.
Love it. Love it. So where do you look for inspiration and idea flow?
You don't just mean people, you mean idea flow.
Yeah.
Yeah, like I mean, I still go to scientific conferences.
Okay.
It's really important to be in touch there. It's not just finding people, but finding the ideas. I do some research on my own. I also run a nonprofit that I started about what is it now, 7 years ago, which is kind of the main open source quantum technologies nonprofit, kind of like Linux Foundation for quantum techs. And we do research there, and you know, I get to just talk directly to hackers there, and I don't always tell them I'm a VC.
No, that's perfect. All right. So what do you read on a consistent basis that you couldn't live without?
Ooh. The Italo Calvino's 6 Memos for the New Millennium.
Nice. Nice.
That's an answer I can say we've never heard. So that is a unique one. Love it.
Yeah.
All right.
You know, it's probably a little bit. Wait. We've probably got more questions, but I'll tell you, it's 6. It's he's a great novelist, fabulist, poet, and he's writing about 6 values that matter for literature, like why literature values, and they're like short essays. They're about exactitude, consistency, visibility, lightness, and multiplicity. Though he died before writing that consistency one, so it's a little fun. But and those are values in literature, but I think they're values that have helped me think about life. So I find myself returning to it a lot.
Amazing. Amazing. All right. What do you do for fun?
What do I do for fun? I quantum stuff, quantum research, quantum hacking on quantum stuff.
Hacking. All right.
Yeah, like, I mean, okay, look, so my most recent paper.
No rowing. I mean, I see the oar behind you. So no rowing.
Rower, a little bit. I do some alumni thing. Did Heather Charles a couple years ago. Yeah, I rowed for a long time. But yeah, I mean, one of the side projects recently is we put out a paper with some collaborators in my foundation on how to use quantum computers to ask some physics questions. So it's not, obviously there's commercial applications of all this stuff, but there's also science we're going to get access to when we have better quantum tech. And I've been working on some stuff there.
All right. So what's your favorite secret spot to eat back on campus at Yale?
Oh, Yale?
Well, yeah, in the Yale vicinity.
So New Haven is known for its pizza. And there's kind of everyone's like, are you a Sally's or a Pepe's person or something like that? Nah, don't go to Sally's or Pepe's. You want to go to get a basic slice of cheese at what is clearly a converted gas station called Brick Oven Pizza.
Okay.
Bunch of wood outside. It's a wood-fired thing, and their basic cheese slice is fantastic.
Perfect. All right. So where do you escape to when you need to recharge the batteries?
Well, I maybe with the Calvino thing. I like literature, I like fiction. So that's like typically where I go.
All right. So, and you may answer this the same way. So if you could have dinner with anyone, alive or in the past, who would it be?
Ooh, anybody alive or in the past? Okay, I give a stochastic answer to this. I'm a non-deterministic. I've been asked this question before, and I give different answers. But the name that's popping into my head right now is von Neumann, and
yeah,
maybe it's because we've been talking about computing, but I feel like I really could use his help. Because a lot of really smart people of his contemporaries said that, he was like an alien to them. I remember a particular anecdote I can't remember who it was. It's probably another Institute of Advanced Study person who said, he saw John von Neumann at a dinner party talking to one of this physicist's children. And he was great. He was talking to that child like they were an adult, like he was really interacting with them. And the physicist realized that John von Neumann, when he was talking to every adult, was doing the same thing.
Wow.
And he was like, wow. So he's an intriguing character, and I would just want to see how his mind works a little bit in dialogue.
Love it. All right. Last one. What's the most impactful book you've ever read?
Oh,
and like I got bookshelves behind you, got bookshelves behind, X got bookshelves. We all have bookshelves, but So
Pick which. The honest answer is probably Quantum Communication and Quantum Information by Mike Nielsen and Ike Chuang, which is like the Bible textbook. It's now unfortunately a little out of date. It got updated in 2010, but like that's what opened this up for me. It's an excellently written book, great exercises. It was written at a time when you could fit the whole field into one textbook that like an undergraduate with some linear algebra could pick up. And it's changed my life.
awesome. All right. Thank you for that. And well done.
Yeah, no, well, it's great. It's great to get to know you. I would be remiss without getting you out of here with one kind of final question or takeaway. Give us your all-time favorite scientific movie. I've got a penchant for this, and it's hard for me to pick one. So maybe as I will say some will come to mind. I love Imitation Game and kind of the birthplace of AI, and of course, going back to Beautiful Mind and my now New Jersey roots, and the beauty that was all the developments out of Princeton, and obviously what followed in quantum years later. But what kind of sticks out? What shall we watch this weekend as a good science movie before we head on out?
Yeah, I'm gonna slightly dodge the question because the science movie I want hasn't been made yet. But it's like if I wanted to pitch a movie, this is the movie I would pitch. It's based on I read a lot of science fiction books though, and so my favorite science fiction author is Greg Egan, and he's a fantastic mathematician as well. Anyway, he's way out there, and the book is called Quarantine, and it's got like 90 sci-fi tropes from like 92, 93, something like that, and all of a sudden the sky goes dark, and people don't know why. And I'm a little bit scared to give the spoiler of why, but what happens in the last third of the book is an action sequence set in superposition. It's fantastic. There's a lot. Like it's based on quantum mechanics, and it's a person who can like shift. It's amazing.
Love it.
And we should after Tenet, maybe these kind of movies could be.
Love it.
I would.
Well, you must have loved Project Hail Mary or the Hail Mary Project, and that is coming to movies, so Quarantine might be next.
Yeah. So Mark, we've got our work cut out for us. I think we have the resources on this podcast to at least get some shine on this, because I think that would be an excellent plot and at the same time very educational. So we'll have to invite you back, to see what's going on the investment side, but also to see if we made some progress towards this goal.
All right.
And thank you so much for joining us, Will. Absolute pleasure. And we'll have to invite you again soon.
Thank you.
Thanks, Will.
Thanks so much. We'll remind our listeners, as always, rate, review, subscribe, and to stay current. Thank you for joining us this week on Digital Currents. Check out our links to our website and social media in the show's description box. Please make sure to subscribe if you like what you hear. And remember, stay current.
This podcast should not be construed as investment advice nor solicitation for the sale of any security, advisory, or other service. Investment themes and ideas discussed may be owned by funds managed by the host and podcast guests. Any conflicts at the time of production have been mentioned by the host but are subject to change. Listeners should consult their personal financial advisors before making any investment decisions.